I'd like to welcome Phil Wookey here. Phil's a professor at the University of Stirling in ecosystem ecology. I have to read this bio because it's really funny. Well, not the first part. But Phil's an ecosystems ecologist and biogeochemist whose research is focused on high-latitude ecosystems and environmental change. He's worked in the Arctic and subarctic since 1993, and before he went to Stirling, he was at Uppsala University in Sweden. Phil is currently the chair of the Terrestrial Working Group of the International Arctic Science Committee, and prior to that, chaired the International Tundra Experiment, or ITEX, which some of you might be familiar with. And I don't know if you're going to talk about ITEX.
I'll talk a bit, yeah.
A little bit? Okay, good. So Phil won in 2004 the Bergstedt Prize from the Royal Society of Sciences in Uppsala, Sweden. And this is the fun part now. Phil is passionate about the North and attributes his love of cold, snowy, and wind-swept places to his maternal heritage from Sunderland in the north of Scotland, going on expedition to North Iceland as an undergrad and reading Jack London novels. Phil's prospect of completing the Munros, the highest of Scotland's mountains, 282 mountain summits, named after the man who first catalogued them, Sir Hugh Munro, took a temporary step backwards upon accepting a job in Sheffield, but he soon realized the error of his ways and moved back to Scotland. As colleagues and friends would attest, however, Phil is now built for comfort and not speed. He is a sedate skier, a mediocre badminton player, and would love to learn fly fishing, but never really has the time. His top tip for fieldwork reading material would be The Worst Journey in the World by Apsley Cherry Garrard. Is it Garrard?
Garrard, yeah.
Garrard. Yeah. First published in 1922. This is about polar exploration, science, and suffering, told by someone utterly disarming, brave, and not comforting to the stereotype of the genre. Phil finds this compelling narrative puts the occasional bad day in the field in true perspective. So I'm really pleased to have Phil here. We've known each other through various scientific conferences for a while now, like maybe even 10 years.
10 years plus,
so
yeah,
it's great to have him here and to bring another dimension to our Arctic Speaker Series, which this year so far has focused a lot on the social sciences. So.
Awesome. Thanks so much, Mary Beth. Thanks so much to the Arctic Institute folks for inviting me. It's a real pleasure. And it's an honor to be here before you today. Without further ado, if the sound's right, I'll crack on. So the title of my talk today is Biospheric Feedbacks and the Arctic Amplification of Climate Change. And the point that I really want you to leave with at the end of this short time together is that ecosystems, vegetation, soils actually matter in terms of how the global climate system works. And I think nowhere is this more clearly expressed than in the high northern latitudes. And I hope that I can take you on a bit of a journey now that includes some of my own research. And I apologise if I go quite fast. I'm trying to paint a picture here rather than get into too much detail. But if there is a point where you want to just stop me and say, hang on, Phil, I didn't quite get that, can you just run through it? Then I certainly will. And please feel free to. And I hope you can have a chance to talk a little bit afterwards as well, maybe answer some of your questions. So here we go. So effectively, you'll already be very well aware that the Arctic helps to keep the planet cool. And there's very obvious and clear ways of viewing that. And that's, for example, at this time of year, with the massive snow and ice cover that we have. And that's very important in terms of reflecting solar radiation back to space without causing warming. It also, however, when we talk about ecosystems, it stores a huge amount of carbon, actually, as well. In Arctic soils, for example, there's twice as much carbon there than is present in the whole of Earth's atmosphere as carbon dioxide and methane. And hopefully it'll become apparent why this is important later on. And this is kind of just a bit of a patch of low Arctic tundra in Northwest Territories here in Canada, just kind of illustrating that. We've got our typical features here we've got our polygonal tundra here with ice wedges and so on there. We've got quite deep organic rich soils as well. So they're two key factors. It's warming fast, okay, at twice the rate of the rest of the planet. This is a very important point about these high northern latitudes. And based on measurements that we have from records on the ground, but also increasingly satellite-borne records as well, we know that the situation's warming very dramatically. There's an Arctic amplification of warming, and here you can see this very, very clearly in the high northern latitudes. I think perhaps even more clearly here, this is the 1950 to 2014 temperature trend, here. This is the trend in degrees Celsius change per decade along the scale here. So the warmest colours are a warming of 0.5 degree per decade. And we can see that this is manifest most clearly in the high northern latitudes and in the inner continental areas as well. And this is the temperature anomaly for this period for the year 2016. We can see just how clear the warming is here. And the actual scale, just for information, these reds, we're talking about 2 to more than 4 degrees Celsius above the long-term mean conditions. So there's an Arctic amplification of warming, as I've mentioned. This is perhaps most clearly expressed, and the most obvious feature of this is the change in sea ice. So here we've got the long-term series. It goes back to 1980. We have, for example, declassified military submarine data that go back earlier, but this is the reliable records that we have here. And there's a very, very clear downward trend. Of course, it varies from year to year, and there are some years where Donald Trump would say, oh yes, it's recovering. Okay, there's no such thing as global warming. So that's the situation there. There's a very, very clear trend. 2012 was the lowest September sea ice extent, but these are the data for 2017. The little, I think you can probably just spot a pink line there. That's the actual median ice edge from 1981 to 2010 here. So last September, we were down by 1.5 million square kilometres of sea ice cover. It's not just the cover of sea ice, it's also its depth and the extent to which it's multi-year ice or single-year ice. So this is changing very fast. And this amplification of change is related to several different factors. I don't want to go into too much detail here, but perhaps the most obvious one is this albedo effect, this reflectance that we have of ice and snow cover, where effectively if we've got a new, fresh snow cover, that can reflect about 95% of incident solar shortwave energy coming in is reflected straight out to outer space without causing any warming whatsoever. Okay, if we change that to an open tundra surface or even open sea, there's much, much more energy is absorbed into the system. So that's important. In the Arctic, more of the extra trapped energy goes directly into warming rather than evaporation. That's another factor. The atmospheric layer is thinner in the Arctic than the rest of the planet up to the tropopause. That has to warm is shallower. And as sea ice retreats, the solar heat absorbed in the oceans is much more easily transferred back to the atmosphere as well. So that's another one. And there's alterations also here, 5, in oceanic circulation too, that can increase warming. And that relates to big circulation patterns, for example, in the North Atlantic Drift as well. So there's lots going on in this area. And an obvious, as I've mentioned already, the obvious positive feedback is this albedo effect. So imagine a snow-covered low Arctic landscape. This is Trail Valley Creek in the Mackenzie Uplands in Northwest Territories. Snow-covered, most of that energy coming in from the sun is reflected straight back. And the difference between these two arrows is small. That's what's actually absorbed. Whereas if we then take the snow away, what we have is effectively a substantially less reflected, because this is a darker surface, and therefore we have more energy absorbed here. So that's, I think everyone understands this one, yeah. So it's a very straightforward one. And so there it is. So yesterday, my journey across from the United Kingdom followed pretty much this Great Circle route. We're just off the map here at the bottom. And from the point where we left, really, the west coast of Iceland, all the way here, the surface was snow and ice. Okay, a little bit of open water going over Baffin Bay in ice leads and so on, but this whole distance, this is 7,000 kilometers, was pretty much ice covered. And this whole area is important, obviously, in terms of keeping the planet cool. Okay, so I think I've probably made that point. We had some beautiful views from the aircraft as well of gyres. This is sea ice here. This is off the coast of Greenland. I think this picture was taken in October 2012. So you can see very clearly this snow cover is a much brighter surface reflecting more energy back. So I think we've established that one, okay? Awesome. So there's also as well, and this is my interests really relate to ecosystem processes rather than these kind of physical feedbacks and so on. We already have signs that terrestrial vegetation, so plants and plant communities on land, they're also contributing to warming because as we get taller shrub tundra, we get trees encroaching onto areas that were open heathlands, that kind of thing before. We change the reflectance of the surface and we change the surface roughness as well, which causes warming nearer the ground. We have a reduction in wind speeds and so on. We break up the planetary boundary layer. So there's all sorts of interesting things as well. These are biophysical feedbacks, really. So what's going on at the moment is there's various studies that suggest that we've got an increase around the Arctic, although there are gaps in the data, in the cover and the height of deciduous shrubs. So things like dwarf birch, some of the alders, green alder that we have in the Arctic as well. We also have indications in very large areas that we've got encroachment onto tundra heaths by deciduous trees. So that's certainly true in the European Arctic, where we get mountain birch moving into areas that were previously Arctic open tundra. So these are potentially quite important in terms of the biophysical feedbacks on change. They affect the snow drifting patterns, particularly at this time of year. They affect the darkness, the colour of the surface. You know that living in Calgary, just looking at areas that have trees, certainly if you're flying over it, are much, much darker, and shrubs as well that are poking above the snow layer. So all of these are important. And then on top of this is we've also got some increasing indications, and my own research is showing this, that if we get more productivity, more photosynthesis in the Arctic, that might not necessarily mean that we store more carbon, because what can happen is if you switch vegetation type, you can end up with fundamentally different processes occurring in the rhizosphere, so around the plant roots, which effectively can rapidly accelerate the decomposition of carbon that's there in the soils. So there's all sorts of interesting interactions going on, and I'll try and just touch on a couple of those as we go through. Okay, so one project that I've been involved in that's already been mentioned was the International Tundra experiment, and I'm still involved in that, and I'm hosting the 19th annual meeting in Stirling next month, which is a pleasure. It's been going since 1990, so it's been a bit longer than that. We've had 1 or 2 years break. But this particular program has produced some very, very important works on the responsiveness of tundra plant communities to warming. And we've done little experiments using hexagonal glass houses and plastic cloches and so on, literally out on the Arctic tundra, to try and understand how these ecosystems respond to warming. This was my first billet. This goes back to 1991 when I first started working in the Arctic. This is a picture taken, I think, on the 21st of June in Ny-Ålesund, which is, the Norwegians will tell you this is the most northerly community in the world, at 79 degrees north. The Canadians would have a different perspective on that, I'm sure, as would the Greenlanders. But anyway, this is me arriving for my first taste of proper Arctic fieldwork. And at that time, this was where I worked. So you can see this little patch of Arctic polar semi-desert vegetation with these little pods on there. They're little greenhouses. So it's quite naive in a way, the experiments, but we were effectively with these, they had holes in the top, we were producing a 3-degree warming here and looking at what that did to the plants. We were also adding nutrients and adding water as well. But the whole thing put together, so in ITEX there's been a lot of different studies where we all got together back in 1996 and subsequently at various intervals, put all our heads together, put all our data together and analysed them together using what we'd call meta-analysis. I don't need to go into the details of that at the moment, but that's where you pool all your data, you look at parameters in warmed plots, so that's experimental, and control unwarmed, and manipulate the data that way. And this shows the responses, and I'm not going to go into too much detail, you'll be glad to hear, on this, but just really to point out that this, anything above 0, this is all compared with the control, so unwarmed ambient plots, is an increase in response to warming. Anything below 0 is a decrease. The things that really thrive with warming are shrubs. So shrubs total there, deciduous, evergreen, dwarf, and so on. So they do well. The losers are things like the ground layers, so things like mosses, lichens, things like that, okay? And it's possibly in our experiments to do with a lack of water because we exclude some incoming precipitation, so it might be an artifact. But we very clearly see, so this is a paper produced in 2006. This is pooling data from 61 experimental studies, up to 24 years of duration. And the results parallel what we measure in nature. So we can experimentally warm and we see plants responding to this. Often their reproductive performance is much better. Their seed settings improve. They generally grow taller as well. It depends which plant functional type we're dealing with. But what we see parallels what we measure out in nature. So this is measurements on the ground. of long-term plots, but also by satellite using something called Normalized Difference Vegetation Index, which is simply, in simple terms, it's a measurement of productivity that we can derive from spectral characteristics from a spaceborne satellite system here. And what we have is a change in phytomass here. So this is a change in the amount of productivity in grams per meter squared per year. Okay, and this is going from 1982 to 2010, and you can see this is all above the tree line. That's why we're just dealing with this, the sort of Arctic rim here. This is all Arctic tundra. Southern end of this is into the boreal forest, but you can see generally that's getting greener. It's getting more productive. Now, people have said, oh, that's great. If we warm the Arctic and it gets more productive, it's going to be pulling in more carbon dioxide from the atmosphere into plants through greater productivity, more rapid photosynthesis, okay? And that all sounds logical, but I'll try and challenge that idea a little bit later. So we've got these satellite-borne measurements. We also have measurements on the ground from this paper by Howie Epstein, where they've actually gone to plots in various locations around here just to check that the satellites are telling them something sensible. So here they've measured Normalized Difference Vegetation Index here on the ground, and then they've harvested these plots and chopped them all up and dried them and weighed them. And there's a very clear relationship between this vegetation index and biomass, okay? So the Arctic's getting greener, apparently, okay, which should be a good thing. And there's projects, for example, for International Polar Year, like the greening of the Arctic. That all sounds lovely because it all suggests that, oh, great, this system's getting warmer, it's going to trap more carbon dioxide from the atmosphere. So what's it look like on the ground? Well, this is Trail Valley Creek. This is a subsidiary called Siksik Creek, actually, and Trail Valley Creek's just down the bottom here in Northwest Territories. And this is sort of happening over quite large areas of low Arctic tundra as we're getting kind of encroachment by these quite big shrubs. Some of these are older, they're bigger than me. Okay, so they're not just wee things here. And this is dwarf birch, and that's also getting taller. And what's going on here is it's thought that this relates to global climate. Sorry this is slightly involved, this diagram, but I'll just pick out the important bits. So this is from a paper, it's now quite an old paper by Terry Chapin in Science. But he's pointing out here that this matters in terms of regional climate, okay? And so what he's saying here is effectively we've got global warming here. So we've got low latitudes warming, we've got high latitudes warming. In the high latitudes, if we just focus on this part for the moment, if we've got warming, we might have earlier snow melt, which means we've got decreased albedo, that's surface reflectance, which means we trap more radiation from the sun, and it causes warming, okay? So that's a positive feedback. In addition to that, if we have increased growth of some of these shrubs and subshrubs, then that also will decrease surface albedo, make them reflect less, and that contributes to warming as well. So there's a positive feedback going on here. So that's an energy budget one, but the one I'm going to touch on next relates to gas fluxes, greenhouse gases actually. So that's very important, and you can see that it's linked as well with things like less sea ice, again decreased albedo at sea, increased radiation and so on. There's some negative feedbacks. So for example, we might expect the Arctic to become cloudier in the summer as the temperatures warm and there's more open sea to the north as the sea ice itself retreats. And that would be a negative feedback on warming, so decreased sort of net radiation. So more summer clouds as well, potentially round the coastal area, at least leading to a depression in temperatures as well. So there's positive and negatives, but we think the direction of travel is it's a positive feedback overall. Now this paper by Terry Chapin, where this diagram actually comes from, has done all the maths. So they've done the energy budget calculations, and I've got them at the very end, but I thought I wouldn't include them here because it's a bit involved. But it shows that this is actually important. These changes that have been measured over the last 30 or 40 years are changing the regional energy budget. Okay, so another one that I wanted to show, sorry, stay, that's it. Another really neat paper came out more recently by Pearson and colleagues. And this one was really a modelling study of what if we turn the Arctic tundra, okay, from open tundra as it is now. So these colours are sort of like shrubs, prostrate shrubs, so low shrubs and erect shrubs here, into trees and taller shrubs. Okay, so that's here. So you can see here, this is going forwards basically 100 years according to the modelling. And these areas that previously were open tundra are now increasingly being dominated by trees. And what does that mean? Well, it's quite interesting. So that's the kind of direction of travel. As I say, they're modelling what the climate might be in the future and how the vegetation in theory could respond. And you see here in a little bit more detail what it actually relates to. And the greens here and the dark greens are more kind of shrub and tree cover. And you can see here, certainly in Canada, okay, so that's well, there's Hudson Bay there, and then we're talking about, where are we? Okay, so that's Banks Island there, and so on. Very much at the lower end, much more trees there. Same picture along the north coast of Russia here as well, the same sort of picture. Now, when they do the modelling of this is the change in energy receipt basically here, so delta. Okay, so this is surface net shortwave radiation, so the net receipt increase in radiation at the surface to do with this change in vegetation at different months of the year. And this is the equilibrium, so that's assuming that the whole thing changed overnight and we suddenly invaded Arctic tundra with trees and shrubs and so on. We know that's not going to happen because, you know, most trees are not ents that I'm aware of. They're not going to march across the open tundra, okay, and colonize it. They take time. So that's the equilibrium. That's assuming that everything's moved and it's all happy in its climate of 2100. This is the restricted dispersal. So this is a more realistic one, but it's still nonetheless a substantial increase in the receipt of energy, particularly in late spring, early summer, as the snow's melting out. Okay, here, because we've got shrubs poking out above the snow layer and increasing the amount of energy trapped and so on. So there's a good mathematical basis for this. Like I said, I didn't want to get into the details of that because it's kind of quite dry stuff to sort of go through. But it's there. So these physical and biophysical processes are important, but they're not actually specifically what I'm interested in. I like chemical exchanges and fluxes. I like chemistry, I like gases and things like that. That's kind of what I'm really keen to understand, the processes that produce and absorb those. But they're potentially much more complicated to understand. So this, rather than biophysical, like reflectance and surface roughness and these things, the biogeochemical. So what's actually happening to things like photosynthesis, what's happening to methane production through methanogenesis and the opposite methanotrophy, what's happening to soils as they decompose and so on. And they're hard, actually, but they're less obvious feedbacks on warming, but they're important. So here we go. So this area is potentially a massive site of exchange of these gases between the surface and the atmosphere. Okay, there's huge, huge fluxes. The one that I'm most passionate about, in a way, is respiration, soil respiration. Okay, it produces every year, so just the way our soils metabolize and the microorganisms and the small animals and things in there, every year soils release about 10 times more carbon dioxide into the atmosphere than the whole of human activity put together, than the whole thing. So it's really important that we understand what controls the rate of these processes. So that's important. The other one, methane production, is really, really temperature sensitive. If you increase temperature by 10 degrees, you'll cause a 5 times, 6 times increase in the rates of production of methane, okay? So very, very temperature responsive stuff. And the other thing to point out is, so this is a map of this is the Circumpolar soils database. And so this doesn't just cover Arctic tundra, it goes into the boreal. It, broadly speaking, goes into areas underlain by permafrost, which in Canada is what? Under more than half of the actual land surface, I think. And this is the amount of carbon per square metre in these soils, okay? It varies, of course. The darker colours, so into the dark browns, that's up to, and this is in the top 3 metres, and there's potentially much more lower down, frozen in permafrost. 100 kilograms per metre squared of carbon, just sitting there. That's a me's worth of carbon per square metre. Okay, actually a little bit less than me at the moment, but I'm working on that. Obviously not very successfully. Yeah, that's a lot of carbon. Okay, you do the maths, multiply this up. We're talking about an area here of about 21 million square kilometres. Okay. And what is it? Effectively, in some of these areas, so this is dug down to the permafrost, it is effectively a frozen compost heap. Okay, it is a massive pile of carbon in there that's been accumulating in cold and often poorly drained conditions for tens of thousands of years, in some places longer actually, in others that weren't ice covered, okay, during the Pleistocene. So this is really important, okay? So we are talking about here, I have to always remind myself how many zeros. So this is around about 1,500 petagrams of carbon in permafrost regions. And a petagram, okay, is 1 billion tons. Okay, that's 1 billion tons. All right, that's a lot of carbon, okay? And at the moment, it's happily tucked away there, frozen, not metabolizing very fast. But this is, we believe, and we have the measurements to support this is changing quite fast. So, vegetation is just the tip of the iceberg, okay? The analogy here is that there's such a lot going on below ground that we can't measure from space. We can't use satellites to do this stuff. We have to get into the field with our welly boots on and spades and shovels and permafrost drills and actually go and do the measurements. So that's the key thing here. So we've got this vegetation change that we measure and there's been a lot of focus on. It's just half of the story or less. And I'm sorry about the cheesy picture here, but that was kind of really illustrative. So that's some Vaccinium vitis, okay, which is otherwise known as if anyone's from Sweden, lingonberry, okay, that you might put on your meatballs. That's the portal, of course, by which carbon enters the system, okay? But then that carbon can be sticking around for thousands of years, okay? And over the Holocene, so the last interglacial, it's been accumulating but freezing from below as well as it accumulates. It's been, the permafrost table's been rising and trapping that. But what happens next, you know, as we've got this warming? And this whole question of, I'm not going to stick to just permafrost, I'll talk about another example sort of like in a minute, but permafrost is now, just now, starting to grab the kind of like, you know, the public imagination, okay, and what's actually happening. So even in, well, so the BBC, this one's 2015. What's that? Do you really? Mary Beth knows that house. All right, so. You didn't dig a trench, did you there? Yeah. Right, okay. I was going to say that's quite a big trench. This one I loved because you know, my mother's 81 now, and she's a very intelligent woman, but she reads this, you know, a red top, as I call it, the Mail online, or not online, the paper version, the Daily Mail in the UK, which is generally quite right-wing. And even there, so we get this loss of world's permafrost is unbelievable. Melting ice could release devastating quantities of methane and accelerate global warming. So there's a headline there. I found it interesting that it said here online to me, you might like jaw-dropping celebrity wardrobe malfunctions as well. I'm not quite sure why that popped on to mine, but I guess it's sensitive to your browsing history or something. I don't know quite how it works, but I think it probably came up for everyone. But anyway, I'll move swiftly on. So that's the Daily Mail. A more serious note, so this is great. So one of my team just in February this year published a paper in Environmental Research Letters on the way carbon in soils and sediments is moving into fresh water, into drainage waters. And that we do work with radiocarbon on this. We don't actually apply any radionuclides in the field. We just rely on the radioactivity that went into the atmosphere when they did the atomic weapons tests of the 1950s and 60s. And of course, plants thought that was just the same as ordinary carbon dioxide, so they photosynthesized it, and we see it still in the system. But so this article came out on the 1st of March that is specifically about our recent paper in Environmental Research Letters. So I like the headline here, ancient carbon is coming from Arctic soil. It might be fine, but it might be terrible. So I kind of like that. It's fairly inconclusive. But all of this stuff with thawing going on, with carbon from soils potentially finding its way into surface waters and so on, this is quite a big deal. And I did just want to actually show you this one, if I can get this to work. I might need to use the mouse, mightn't I, actually, for this one? Let's just try. I think we're okay for time, so. Can you hear that? All right, that is not a joke. Okay, that's real. Okay, so All right, so what's going on there is effectively we've got thawing going on in catchments around these surface water bodies. We've got trees and peat, so organic material falling into the rivers and streams. Okay, also it's sometimes dissolved as well. That's what our paper was about. So this dissolved carbon and carbon dioxide finding its way from soils into surface waters and then back into the atmosphere, sometimes in very spectacular ways like that, when it ends up on a lake bed and it's just fermenting. Okay, it's got the lake ice, okay, on the surface trapping it, but it's just building up there, waiting for the spring thaw. And that's something that's going on over very, very large areas. Of course, it's part of the natural cycle as well, to some extent, but the question is, are we accelerating this? And so really with this permafrost situation, what we're talking about is we've got surface temperature increasing, vegetation here and thaw getting deeper into permafrost here, which contains a lot of buried and frozen carbon. This starts to decay. Okay, it's this compost heap, really. It's just starting to metabolize. And it goes into the atmosphere as carbon dioxide, or if it's a very wet system, more in terms of methane. And methane is 25 times more powerful as a greenhouse gas per molecule than carbon dioxide. Okay, of course, there's much less. There's 2 parts per million of methane approximately in the ambient atmosphere, and there's 400 parts per million of carbon dioxide. But the methane story is important nonetheless. When I started my PhD, I used to measure carbon dioxide concentrations routinely. And the concentrations back then were 355 parts per million. So in my short working career, we've gone up by 45 parts per million, the atmospheric carbon dioxide concentration, which is, I think, important. Okay, so that milestone was passed 2 years ago. Okay, so we've got this positive feedback loops going on. There's another paper that came out by, Hope and Schaefer in Nature Climate Change that did an economic analysis of this as well. They're talking about melting permafrost costing the economy overall over the next 80 years or so, $43 trillion US. This isn't just to do with atmospheric chemistry changes, it's to do with the damage to buildings and infrastructure, pipelines, that kind of thing that are involved here with uneven sort of like road surfaces, all the repairs that have to go on there. But that's the analysis there. So there's potentially a lot going on here in this story. And here's some pictures from Yukon Territory in Canada. So we've got here melting out going off. Here are very, very ice-rich sediments and so on here, and the whole thing sloughs back. I did have a video showing this happening in real time. Well, it's time-lapse photography, but I thought it was too long to actually sort of show, so I took that one out. But this stuff's happening almost as you watch. These things, this material in this case is ending up in the sea. Where it's going next, we don't know, but potentially it can end up back in the atmosphere, okay, and so on. So this is big stuff. So this is the paper that was featured in the Washington Post in Environmental Research Letters. So this came out, say, the end of February, so it's very recent. So abundant pre-industrial carbon detected in Canadian Arctic headwaters, implications for the permafrost carbon feedback. And without getting too much into the detail here, I just wanted to show you one diagram from this. But first I'll show you where this work was done. I'm sorry this is skipping forwards a bit. Whoa, stop. Oh, it's very sensitive. There it is. Fantastic. So, what's going on here? This is a project that we've been involved in for some years now. It started in 2012. It's sort of wrapping up now. Based in the Mackenzie lowlands, so just to the east of the Mackenzie Delta up here. So here's Inuvik, Tuktoyaktuk's up at the top here. And this is a big sort of UK, North American collaboration. So there's several different people here. I don't need to sort of go into too much of the details here, but Government of Northwest Territories, Montreal, Aurora College in Inuvik and so on. So lots of different groups there involved. And this project, specifically what we were trying to do in this project Hydra, was to look at the whole carbon cycle. So to look at what's going on between the land and the atmosphere and what's going on between the land and the surface waters in terms of greenhouse gas fluxes, and also things like aqueous transport of this is dissolved organic carbon, this is dissolved inorganic carbon, and this is particulate organic carbon. So what's being delivered into surface waters that can then end up as methane, as you saw from Katie Walter Anthony's video there, in these lake basins and so on. What's happening? You know, what's going on? And this is the kind of measurements that can be quite low tech, really. This is my colleague Mike Billett, who's just retired, and he's got a little plastic tray there, a box, inverted, floating on the water surface. It's attached to an infrared gas analyzer that measures CO2. Within seconds of attaching this, you can see the concentrations of carbon dioxide going up to 4,000, 10,000 parts per million, okay, in this box, because this is degassing so fast. So that what happens here is in these surface waters, you've got supersaturated carbon dioxide, okay, in these surrounding catchment in the soils because there's decomposition going on, microbial metabolism, the CO2 concentration is very high. That's fine until it ends up as surface water, and then it's like opening a can of Coke or something, or a bottle of something, you know, carbonated. You're depressuring it, you're degassing it, and it ends up in the atmosphere really fast. And people had really not picked up on this until very recently, that this was even important. So we're now starting to get into some of the details here. And I mentioned that we use, so we're making use of what was a horrific thing, obviously 70 years ago, 60 years ago, 55 years ago, the atomic weapons tests in the atmosphere, which of course have been banned, but they injected huge amounts of radiocarbon into the atmosphere as carbon dioxide. Okay, so very, very large amounts, and plants just photosynthesized it as normal. And so somebody of my vintage as well, I know I'm hot in other ways, but you know, my skeletal structure will be loaded with 14C because of when I was born and when I grew up, because of all that 14C that was rolling around in the system, okay? And we still see this in the biosphere, and we do measurements with our colleagues at the Radiocarbon Lab in East Kilbride in Scotland. This is our main man, Mark Garnett. We have a particle accelerator, a tandem accelerator here that we use, and we can measure the atom ratios of carbon isotopes in very, very tiny samples of gas now and get a realistic indication of what's going on. So in this particular paper, I just wanted to point out, this is surface waters, this is dissolved organic carbon and carbon dioxide, and this is as a thaw period progresses from June to September. And I just wanted to point out, just the top right of both of these panels is the modelled age of this material based on the 14C characteristics of it at the end of the season. And you can see here that all of the yellows and the reds are pre-industrial. So this is carbon dioxide that was fixed before the Industrial Revolution, 1750, that is now finding its way into our surface waters and then downstream potentially into the atmosphere. Okay, so that's what this paper's about. All right, so that's that particular component. So, and that led to that particular research paper. So there's this link between the land and the fresh waters. But when we think about the land itself and about soil processes, this compost heap, this very, very carbon-rich system, when we warm things up, what actually happens to the rates of metabolism? Well, these direct responses of soils to changes in the temperature, in the moisture regimes, they're quite challenging to predict. But we can go back to this fella, a Swede who was based in my old institution in Uppsala for a while, Svante Arrhenius. You've probably heard of the Arrhenius equation, some of you. And he came up with this, not surprisingly. So it's basically chemical and biochemical reactions depend on temperature. And there's roughly an exponential relationship between them. As you warm things up, if the substrates are available, reactions speed up. So he got this quite early on in his career. He got the Nobel Prize in 1903 for nothing to do with this, actually, but for his work on electrolytes and batteries and electrolysis. But this is him on Spitsbergen, okay? Here's your man on expedition. I kind of like the connections, so he had Arctic research interests. But the other one I thought was really interesting is here's a paper that he published in April 1896. Okay, so this is 100 and whatever that is, 22 years ago, if my maths is right, top of my head. He published in the London, Edinburgh and Dublin Philosophical Magazine and Journal of Science on the influence of carbonic acid in the air, in other words carbon dioxide, on the temperature of the ground. Okay, and well, I'll let you guess. So for a doubling of atmospheric carbon dioxide concentration, he worked out that the temperature on the ground would increase by how many degrees Celsius? Any ideas? Any guesses? Close, 3 degrees. He worked out if you double atmospheric carbon dioxide. So this is a long time ago, guys. You know, I know I'm just preaching to the converted. I know it's an echo chamber to some extent. But we've got people that deny this stuff. You know, I use instruments, the infrared gas analyzer, based on the fundamental physical principles of how gases interact with electromagnetic energy. Okay, that's how we measure the stuff. It's just absurd to me that the greenhouse effect was known about in 1826 by a French guy called Louis Gay-Lussac. Okay, Svante Arrhenius published in detail on it in 1896, and there's still people around here that just don't seem to even believe this stuff, which I find remarkable. Okay, so unsurprisingly, when we warm Arctic soils, the rates of CO2 release increase. Okay, so we thaw it, we warm it, we get more carbon dioxide out. We don't see any signs of downregulation. This has been a big discussion. I won't go into the details, but a lot of people have said, oh no, that won't last forever. It will just acclimate. Microorganisms somehow or other will self-regulate their rates of metabolism, which just doesn't make any sense to me at all. Why would they try and save resources? You know, you're a microbe, for goodness sake. You're not a sentient being, you know. But we've had this discussion. So a postdoc of mine actually did some really intellectually twisted work on this, where he proved that this acclimation idea was nonsense. Instead of doing a warming experiment, he did a cooling experiment to demonstrate that. So I'll just put there, soil microbial respiration does not acclimate to temperature. This caused quite a storm in the literature, which I like, not least with one of my former PhD students. That was interesting. I didn't know which side to take. But then we went big, and we got a project that went all the way from the Peruvian rainforest through all sorts of Mediterranean ecosystems, the UK up to the Arctic in Sweden, and we did the whole thing there and got a paper in Nature as a result of that, showing the same thing. Okay, but particularly the Arctic soils are very sensitive to warming. All right, so plant-soil interactions, however, in the rooting zone, I think they're potentially critical in all of this. So, and I don't have much further to go, so that's all right, you don't need to worry. I'm sort of coming towards the end now, guys, so you'd be quite pleased to hear that. So we've got this direct response to warming, both in terms of things like carbon dioxide production, composting really, methane production if it's waterlogged, that kind of thing. But we also have, with changes in vegetation and increased productivity, changes perhaps in plant types growing in various areas, things that can happen in the rooting zone that become really critical, and I'll try and explain that. When we think about ecosystem responses to warming, we know that climate affects plants and their rates of metabolism, photosynthesis, that kind of thing, and plants affect climate because obviously they release things like water vapor and carbon dioxide back to the atmosphere as well. They respire, as we are all doing in the room now when it's dark and the lights are off and so on. We've got a pretty good idea about what controls photosynthesis, plant metabolism. So that's fine. And then climate exerts an independent effect on soils. And as we've seen from previous work and equations from people like Svante Arrhenius, they respond to warming, okay? So that's fine. So we've got a tick there, okay? We know that quite well. We're not quite so sure about soils. There's still quite a lot of controversy about exactly what's going on. But because plants and soils interact below ground as well, there's some really interesting chemistry. There's some sort of chemical magic that's going on down there that we really don't know anything at all about. Okay, so this is really important. So, this is where my current research really is focused. I just want to go back to just mention two key people in my life that it's been a pleasure to work with. My first PhD student in Sweden was Sophie Högersten, who's now in Nottingham in the UK. She did a fantastic job of her PhD across the whole Scandinavian mountain chain, actually. And then Ian Hartley, who was my postdoc in a former project, and now he's an associate professor in Exeter University. These guys have done fantastic work. I mean, really, really great stuff. Specifically, this picture, Mary Beth, you'll recognise this. It's the Lapgate in Abisko in the background there. So this is Swedish Lapland. This is a picture taken out of a helicopter, and effectively you can see there's lots of scrubby birch trees around here. Until you get up to this area, about 700 metres, and you go on to Tundra Heath. So then you'll getting outside the zone where mountain birch forests can survive. This is productive, very productive forest. But if you go and dig holes, it's a classic, what we'd call a podsole profile. It's a classic, very, very thin organic horizon in here, not much carbon. So what's going on? It's really productive, but why isn't there more carbon here? And then if we go into the heaths, we end up with just a massive wodge of carbon in there instead. But it's a very unproductive system. So we've got this kind of paradox going on a little bit here. So, and then part of Sophie's project was, so she had sites here in North Norway, in Finnmark at Jotka, two sites in Sweden called Vassijaure and Abisko. This is one of the wettest places in Sweden, and this is one of the driest, and right next door to each other, to do with the mountains, and Dovrefjell in south-central Norway. What we've got here, all of these sites, if we go and dig lots of holes and measure it, we've got less carbon. This is kilograms per metre squared now, so you can see it's quite low compared to the previous diagrams that I was showing you. We've got less carbon systematically across all of these areas compared to Tundra Heath. And we've done also some magic angle spinning 13C nuclear magnetic resonance stuff as well. A bit of a mouthful that. And this suggests that this organic matter in the Tundra Heath is very decomposable in the right circumstances. So this guy, Ian Hartley, when he was a postdoc for me, did some really neat work using this bomb peak, this 14CO2 spike in the atmosphere of the late 50s and early 60s to understand carbon turnover. And he deduced from this that if we switched from a heath community, so if I go back to this one, with high carbon into a forest community with low carbon in the soils, we would actually lose carbon to the atmosphere. So completely the reverse of what you'd measure by satellite. It gets more productive, we've got trees instead of heath, and the net result is that we just burn this carbon off from the soil, not literally, but metabolically through soil organisms. Okay, so that's boom, going into the atmosphere. Again, it's quite an involved study, so say boom, it's appropriate. It's again based on this peak, this pulse of 14 CO2 in the atmosphere from the 50s and 60s. Where we find it and how much gets respired, we can use to work out how rapidly organic matter is turning over, how fast that's actually happening. Okay, so I won't go into detail, but effectively it's like this. So this is our carbon-rich system, unbelievably, because it's all below ground, or most of it. This is our carbon-poor system, because what we see above ground doesn't match. There's very, very little carbon here. So the direction of travel, this is a potential loss of carbon. And this study was done actually up here, in this area, right in the far north of Sweden. We're not sure the extent to which this is happening all around the circumpolar north. This is Skip Walker's Circum-Arctic vegetation map here. So this is open Arctic tundra. We're not sure the extent to which it's important all the way around. But clearly it's important for us to know. And really this was just to illustrate, I'll just focus on the carbon here. This is the heath, this is the birch forest, the line here is the soil surface, okay, and this is the total carbon here. So heath, a lot below ground, very little above ground. Forest, a lot more above ground, but not enough below ground to compensate. So if we change from this to this as it gets warmer, sorry, excuse me, we move from heath to forest, then we'll lose carbon. And this is what it looks like again on the ground. So, oh, come on. Oh, you suddenly got to the end there. And it isn't quite, but we're nearly there. That's it, stay. Stop it. Good, excellent, right. I'm very clumsy, I do apologise for this. It'll look great on the video. All right, I don't think you can edit that out. But yeah, so if we go from this to this, so we get some Ents colonising and moving out onto the heath, we're going to lose carbon, actually, is the message from this. All right, so I think there was some other stuff there that, I should have mentioned this, excuse me, yeah. That's it, it's skipped a long way forwards, all right, excuse me. So now, just very briefly, just to wrap this up, a former PhD student of mine, Tom Parker, who's now a postdoc, he was briefly in Toolik Lake in Alaska. For his PhD, he was doing detailed work on this kind of relationship. Why are we getting this? What's actually happening? And so he's published several really neat papers now, but he's also pointed out that where we've got very rapid carbon turnover beneath shrubs and tree vegetation, we get low carbon stocks. So that was really a very important sort of conclusion from his work, that as soon as we get trees and shrubs, particularly deciduous ones, something changes. And this is another view of this area, beautiful photo taken by Ian Hartley in the autumn. This is fairly typical, around about September time, how it looks. And good, got it there. Could these organisms be the important sort of like missing link in this whole equation? So where we've got things like birch, aspen, willow, alder, These plants have what we call ecto-mycorrhizal associations, so a particular suite of organisms which are more commonly seen manifested as toadstools on the actual surface. We call the technical term is a sporocarp. It sounds a bit boring really, but if you're a mycologist, that's what you'd say. So these things that we have, so like bolituses and things like that, seps as you might call them in chefy kind of like if you're into your cuisine and things like that. That's what you see and what you eat is just, again, the tip of the iceberg. These have a network of hyphae, very, very thin fungal strands permeating the soil, okay? And also encrusting roots, root tips, and they give the plant nutrients like nitrogen and phosphorus in exchange for being given carbohydrates by the plant. So they're symbiotic, so they're living together, okay, in a symbiotic relationship. And what's happening, we believe now, and we're starting to get the data together, is that when we get these deciduous plants onto what used to be heath, which has a very different type of mycorrhizal association called ericoid mycorrhizas, it's associated with ericaceous plants like heathers and things like that. We switch to ectomycorrhizas, and we effectively, what happens with these organisms, they're much more efficient at exploring the organic matter in the soil. They send out these very, very thin hyphae, and effectively what they're doing is they're mining the organic matter for mineral nutrients like nitrogen and phosphorus, and they're metabolizing, to do that, to release those, they're decomposing and breaking down organic matter, and the net result of that is carbon dioxide in the atmosphere. So when they start colonizing organic, rich, heathy and tundra type soils, these things can start to rapidly metabolize all this lovely carbon in this kind of like Arctic compost heap, and it starts to end up in the atmosphere at very, very fast rates. So Tom's been working on this, and we have a new project that just started last year on this, where we're really now with Swedish colleagues in Uppsala University, the Swedish University of Agricultural Sciences, we're really starting to nail this. So it's quite an exciting time. So I think we're going to have some nice stories to tell. So really going back to this Pearson paper, if we start genuinely to see Arctic tundra switch, so we're going into a shift towards ectomycorrhizas with these green plants and the purple ones, but more of the green over very large areas, this could shift carbon dioxide into the atmosphere. Okay, so not what you'd expect at all from satellite measurements. Okay, it's more productive, but it's less carbon. Okay, and this is potentially, a point of interest. So you've seen that picture before. So I'm sort of wrapping up now. You'll be pleased to hear. So just to conclude, the Arctic's warming faster than any other part of the planet. It's both a sentinel of global change and a key component of the climate system. Okay, that's important. There's very powerful linkages between the biosphere, the cryosphere, or the frozen world, so snow cover, permafrost, that kind of thing, and the atmosphere, and this matters to us all, undoubtedly. Understanding plant-soil interactions, this remains a major challenge for us. Okay, vegetation change that we measure, and a lot of people are measuring, is just the tip of the iceberg. Okay, the tip of the carbon iceberg. Okay, what we can actually measure. Changing hydrology, so drainage conditions, moisture content, and so on, and permafrost thaw, they're going to play a major role in determining changes in ecosystem carbon stocks, as well as net exchanges of carbon dioxide and methane between the land and the atmosphere, but also surface waters in the atmosphere as well. So they're all important components. And my perspective as a field-based ecologist very much is, we've moved on again, excuse me, it's way too early for remote sensing and modelling to replace boots on the ground, okay? We aren't that advanced in our satellite remote sensing images, but they still can't, we don't have X-ray satellites at the moment that can see what's going on below the surface, okay, is roughly what I'm saying here. So we do still need people that are, for mad people like myself, that kind of like to go and get eaten alive by biting insects and be covered in DEET for sort of days on end and not washing for weeks on end and all of those things. We still need that, actually. But I'm too old and I'm too broken to... No, I'm just joking. I'm just being self-indulgent now. Yeah, I kind of... I really love going and working in these places, but I think what's the most rewarding aspect of it to me is seeing people that I've had the pleasure of working with going on in their own academic careers, It's really great. I examined the PhD of a former PhD student of mine, actually Sophie, whose photo I showed. Her first PhD student, I was the external examiner for as well. So it feels like my kind of like academic grandchildren, you know, already. I know it doesn't take quite as long, you know, obviously, to get your own PhD and supervise another one. But that to me is really important, that we do, you know, leave space for people. We need this. We need people actually to be in the field. We can't do this all in virtual reality. Okay, it does actually need people to do the hard work, the digging and things in the field. And with that, I really appreciate the opportunity to come here. It's been awesome. There's an irony, the fact that I'll have travelled 14,000 kilometres by air to get here, for which I feel duly. I couldn't believe it. I could carbon offset that for £1.50. Does that? I don't even understand how that works. I just don't believe it. But anyway, it's a pleasure to be here, and there's more to it than that. And thanks so much for your attention. I really appreciate it. Thank you. Oh. And I didn't even do the acknowledgements bit, so that's always really bad, isn't it? It's a whole team of people over the years that I've worked with. It's been a pleasure. And does anyone know the Yukon Brewing Company in Whitehorse? Yeah, we had to ration in the field because that's two colleagues. A prize for anyone that can guess which beer that is. I think that is Yukon Red. Yeah. Is that Ice Fog? I don't. Anyway, that's a slight aside. We managed to have one beer every other day in the field because of the weight limits on the helicopter, because they just drop you by helicopter and come back 10 days later. And the scary thing is, you know, whether you get a situation where you wave goodbye to the helicopter and then someone says, "Where's the matches?" You know, and you want to make a cup of tea or something like that. So, thankfully, we've never had to call them back. That would cost us about 6,000 Canadian to call them back for a box of matches. That would be the most expensive box of matches ever, you know. But cheers, guys. Really appreciate it. Thank you.
Do we have any questions? Thanks, Phil.
You're welcome.
I have a question, actually.
Go for it.
So the argument is that the mushrooms, I'm just going to call them mushrooms, that mushrooms,
The sporocarps. Yeah.
The mushrooms are, are they respirating carbon? Like, okay, so and you can measure it?
Yeah, well, yes, you can, but more generally, we're just measuring the whole thing. So it's not just the mycorrhizal organisms, but it's the bacteria, some of the small soil animals like springtails and mites, things like that. We don't get many earthworms in these systems. They're not really suitable. But you do get some, but the densities are very, very low. But yeah, you can measure this. You can certainly do that in the lab. But so what they're doing is effectively they're wanting to give the plant something for their keep. So the plant's giving them available carbohydrates like, you know, reducing sugars, things like, you know, sucrose and stuff like that. And what the fungus has to do is it has to mine the organic material around it to get mineral nutrients like nitrogen and phosphorus, and then it will give that to the plant. So that's what's going on. So the plant's giving it lovely carbon, like candy. The soil it's surrounded in is like just kind of, what's the lowest quality food you can think of as a really bad example of something that no one really wants to eat, but they have to? What's that? Okay, well, that's what the hyphae are surrounded with, but they've got to break that down to get the mineral nutrients out of that. So they're being given a subsidy by the plant of goodies, of yummy stuff, but they're effectively in this very low quality resource, but one that contains the mineral nutrients. So that's what's going on. But to get the mineral nutrients, they have to break the chemical bonds, the carbon-carbon bonds, and then that's it. That's being oxidized, the carbon dioxide's going in the atmosphere. Yeah. Well, if you do the modeling, sort of worst case scenarios, you know, and there are some out there, it is significant. You know, it is, you know, it's not something we can ignore. You know, it doesn't appear to be something that, you know, it's a completely runaway process, because the permafrost is not it's not going to melt anytime soon. I shouldn't say melt, I think the technical term's thaw. Yeah, I get told off for that. Melt's got to be actual frozen liquid, you know. So that's going to take decades and centuries, but nonetheless, you know, there's so much carbon there that these processes, whether plant photosynthesis can keep up with those losses through composting, through metabolism of this soil carbon, that's another thing. And that's why we need to understand what's going on below ground. So I'm not preaching Armageddon scenarios here. You know, it takes time for this stuff to happen, but it's measurable over sort of 2, 3, 4 decades. People like Vlad Romanovsky, they have very, very clear measurements of these changes. And we measure active layer depth as well. So we measure how deep the thaw goes each summer. And the best time to do that's usually about the end of August. It's about as deep as it gets. And that's getting deeper and deeper over quite large areas. Good data actually from Russia on that. Yeah. So I hope I've managed to at least give you a bit of a flavour of some of these things, and I hope it wasn't crashingly dull as well at the time. And I do apologise for it's me being ham-fisted with the controls here. I think they need a very light touch, and that's not me. But thanks very much, folks. I don't know if there's any other questions, but.